Hello everyone, my name is Haijun Wang. I'm from Nation. My paper is Typestate-Guided Fuzzer for discovery user vulnerability. Fuzzy technique is an automated software testing technique which provides invalid, unexpected, or random data to a program. The fuzzy techniques are mainly divided into two types. One is generation-based fuzzy. It generates inputs from templates such as grammar specification. The other type is mutation-based fuzzy. It randomly mutates inputs from seed test case. This is also the most popular fuzzy technique. Since fuzzy techniques are very popular, there are still some challenges we should overcome. This is the general workflow of fuzzy technique. One important component is coverage information, because it is determine which seed would be put into seed pool for further mutation. A big challenge is whether the existing branch coverage is enough to detect all vulnerabilities, such as user after-free vulnerability. We use an example to illustrate. In this program, at 940, it uses the freed memory. Therefore, this is a typical UF vulnerability. However, for this program, we use the branch coverage guided fuzzer such as AFL. We did not find this UF within 24 hours. In this figure, we can see that for test case can cover all branches. Therefore, the late test case would be discarded. As a result, AFL has little chance to detect this UFL. To expose this UFL, a test case should cover 9s, 4, 7, 10, 40 together. To this end, there are two challenges we should overcome. One challenge is how to identify the above operation sequence. The second, how to generate a test case to cover this operation sequence. Intuitively, to detect this UF, we should generate a test case that can cover 9, 7, then 9, 10, and then 9, 40. This is the ideal way to detect this UF. Of course, this is also the target of our approach. Based on this ideal way, we developed the Typestate-Guided Fuzzer. In this section, I introduce our Typestate-Guided Fuzzer. Our approach is divided into three components. One is static type state analysis. The second is instrumentation. The third part is fuzzy loop. In the later three slides, I'll introduce them in details. In the static analysis, one input is type state property, which describes the property of vulnerability. The left figure is the type state property of UF. Based on this type state property, we can identify the operation sequence. For example, 9s, 4, 7, 10, 40, which violate this type state property. Based on the operation sequence, we instrument the program. Our instrument is divided into two steps. In the first step, we instrument each statement SI to determine whether SI is executed. In the second step, we retrieve the execution information of SG, which is before SI in the operation sequence. Besides, we also introduce the information flow entropy to build the relationship between input bytes and program statements. Therefore, we know where to mutate the input bytes to reach some program statements. In the end, it is our fuzzy loop. We introduce three optimizations. The first is seed selection. We select the seed that cover more operation sequence. The second is mutation strategy. We prefer to mutate inputs that relate to more operation sequence. The third optimization is feedback. We do not use the branch coverage. We use the operation sequence to guide the fuzzy process. The above three optimization greatly improve the effectiveness of our approach for discovery UF vulnerability. In the last section, we evaluate our approach. Since our approach introduces the static analysis, we evaluate the overhead of static analysis. In the column OS, we show the number of identified operation sequences. In the last column, we show the time overhead by static analysis. On average, the time overhead for the static analysis is less than half an hour. Therefore, the overhead of static analysis is acceptable. This table shows the time to expose UFL. From this table, we can see that our approach performs best in almost programs. The last three rows show the speeds up our approach achieved compared to other fuzzers. At least in this table, we can see that our approach greatly improves the effectiveness for discovery UF vulnerability. Since the fuzzy technique has randomness, we also conduct statistical tests. In this table, we can see that our approach significantly outperforms other fuzzers in most programs. In the last three slides, we show the operation sequence coverage over the time. In these three slides, we can see that our approach is also outperform other coverage-based fuzzers. This is also the reason our approach can find UF vulnerability faster than other fuzzers. That's all. Thank you.